Alright, here we go. Today we got inverse functions. The diagram shows a relation R and its inverse over here. So if you look kind of closely at these, really all that's changing is the domain and range are being swapped. So that's actually what an inverse is. Notice an inverse to a relation inverts the domain and the range of that relation right there. Consequently, the domain in the domain of the relation is the range of the inverse, and the range of a relation is the domain of the inverse. As far as the notation goes, this is kind of important here, especially for like tests and quizzes. We're going to call a regular function fx, but then the inverse function it looks like it's being raised to -1 right there. We call that the inverse function there, and that's just the notation we use there for that. So let's think about kind of what that looks like here. So what is the inverse of relation S right here? So all you got to do is just swap the x and y values around. So our y value is going to be -1, 0, 2, and 3. And then our new y values are going to be 0, 2, 3, and 4. Right there. How are the graphs related? So let's do this here. We'll color code them here. So we'll do the original relation S right there. We'll do that here in blue. So 0, -1, 2, 0, 3, 2, and then 4, 3. So I guess kind of like that there. Don't worry about connecting them. We're not, it's not a straight line or anything. So, all right, the next one here, if we do that, we got -1, 0. You got 0, 2. You got 2, 3. And then you have 3, 4. There, kind of like that. And what can you see about the graph S and its inverse here? So if you kind of need to tilt your paper, and I know you can't really do it on here on the screen, but if you kind of tilt your paper here, you can go and actually see that an inverse function here, it's like it's a reflection. It has line symmetry, but it's kind of across this line here, or y equals x, right there. So it's a reflection across that diagonal line, with the slope of 1 right there. So that's graphically or visually like what an inverse would look like right there. All right, let's do this next one here. What are the graphs of t and its inverse looks like? All right, so this first one's t, so we'll call this next one t inverse. I guess, here, let's do this instead. X, y. All right, so like before, all we got to do is just switch the domain and range values. 0, 1, 2, 3. And once again, I'll color code these here. I'll do the first one, I guess in red. 0, -5, way down there. 1, -4. 2, -3, and then 3, -3. So kind of like that. Guess since I already have this other one in purple, we'll use that. So we got -5, 0, -4, +1, -3, 2, and then -3, 3. Wait a minute. Oh yeah. Looking at that, it's kind of weird there. And that there's the same things going on like we were talking about earlier. The original function and its inverse right there, those are going to be reflected across that diagonal line y equals x. So that's a big thing with inverse. Once again, switch x and y. Now as far as doing it with equations here, it's got a lot of similarities, or it's got that main idea, switch x and y here. So what we're going to do is start out, first of all, I'm going to rewrite it as just y equals 2x plus 6. So then when I say switch x and y, I literally mean switch the y to an x, and then the old x to a y. And then we're going to isolate our new y variable, or basically solve for the new y. And we're going to do this here by subtracting 6 from both sides. And be careful, x and 6, those aren't like terms, so we just write it as x minus 6. You got 2y, and then divide both sides by 2. You can just write it as x minus 6 over 2 and equals y. And then we got to go put it back into the fancy notation. So we're going to say f inverse equals x minus 6 over 2. And that's just the best, I guess, way to write it out there. And then actually, too, it's going to help us for graphing here. I'm going to actually write it like this. I'm going to write it as 1/2 x, dividing x by 2, 1/2 x, and then minus 3. So that'll help us graph when we do that here. Graph the function and its inverse. So here's our inverse here in red. Whoops. We'll graph the original right here, 2x plus 6. See what those look like. So 2x plus 6, I guess it's a little bit off the graph right there, so it'll be kind of up there. A slope of 2 tells us to go up 2 and over 1, and obviously you don't really have any room to do that, so I'm going to go down 2 and left 1. So it still has that positive slope right there. I guess we'll draw the line connecting it. And then let's see what this other one looks like here. So this other one here starts at -3 on your y-axis there, and then it's got a slope of 1/2. So up 1 and over 2. So kind of like that. And then notice once again, if you kind of twist your paper a little bit here, it's a reflection across this y equals x line. Alright, so that is it right there. Oh, as far as labeling them, yeah, it's good to label these here, so I'll put f inverse right here for that one, and then I guess we can just put fx for this one right here. And that's how you label them. So not too bad. Switch x and y, solve for y. Big thing that some teachers bust you hard on is getting the notation. So instead of saying y equals that, put f inverse right there, and then you'll be good. Okay, so now new vocabulary here. You got one-to-one functions and their inverses. So you know that for any function f, each x value in the domain corresponds to one y value in the range. All right, so here's a new one. It's called a one-to-one function. So let's not make that look like an A there. All right, so a one-to-one function. It is also true that each y value in the range corresponds to exactly one x value in the domain. So basically what it's saying is it's a function both ways. The inverse is a function and the regular relation is a function. They call it one-to-one. Each x value has one y value and each y value has one x value corresponding to it. A one-to-one function, f has an inverse, f inverse x right here, that is also a function. If a function is not one-to-one, then the inverse is not a function. That's basically what that is saying right there. So a lot of vertical line tests and that type of stuff here when we're looking at these graphs. So they give us the graphs here. So this first one here is x squared. There it is right there. And then if you switch x and y and then resolve for x right here, this is what it looks like here. It's the square root of x. You got a positive and a negative version to kind of get you that part going up and that part going down right there. So which graphs are function fx and or f inverse x? So your original function right here, if you do your vertical line test, that is a function. So that one is a function. But if we go and do our vertical line tests on our inverse right there, it's not a function. Not a function. So if that's not a function, then we cannot say that the graphs are one-to-one. Is fx one-to-one? No, because its inverse is not a function. Note if fx is one-to-one if it is a function and if its inverse is a function. And since the inverse is not a function here in this case, we say it's not one-to-one. So this is like kind of the main thing that's messing us up here. Okay, so something we can do to see if an inverse is a function, instead of like regraphing it, is doing something called the horizontal line test. So the horizontal line test helps us determine if the inverse, not the original function, but the inverse, is a function or not. I think we might have an example where we go and do that here in a second. Okay, sorry, I had to get my graphing calculator going here for this next one. So for this next one here, we're going to graph the square root function right here, and we hadn't seen too many square root functions, kind of weird looking. Just a regular square root function kind of looks like this here, where it's just square root of x, and it actually, like if you're going to graph it, it kind of looks like a sideways parabola, but only half of one right there. So we're going to look at this one that's got a little bit more action going on. You would have a graphing calculator on like a test for something like this here, so that's why I have that. So I'm going to see if I can move this here for a second. We're going to go and type that into your graphing calculator. So if you have your graphing calculator, to graph anything, we're going to hit the y equals button, and we're going to type in the function. So it's square root, and then of 2x minus 4. So 2, the x right here next to alpha, or the green button, and then minus 4. Make sure you use the minus 4 and not the negative 4, because that will change what the graph looks like. And then press the right arrow to get out of under the radical. And then we're going to hit graph. And there's what it looks like right there. And I think I have my tables messed up here, it looks like. So I'm going to fix a setting. Don't worry about this here. You probably shouldn't need to do this here. And if I hit second graph right there, I can look at the table here. Oh, actually I have another setting messed up here. One second. You can change where your table starts at right there, starting it at 0, and then how much it changes is right there. So I need to change by 1. That's kind of what's going on. Most of your calculators won't be messed up there. Okay, so then it looks like the first point there, you got a few errors, and that's because the graph doesn't go too far to the left. So it looks like it starts here at 2, 0, and then you got a couple other points there at 4, 2. Let's see if there's another nice one. And 10, 4. Alright, so we're going to go ahead and plot all 3 of those points on our graph here. So I'm going to pull this back up. See if we can get that going here. So we had 2, 0. Let's do these by 2s so I can fit it. 2, 4, 6, 8, 10. 2, 4, 6, 8, 10. So we had 2, 0. There was a point there. Oh, I can see it here to the side. We have 4, 2. And then we had 10. Oh, whoops, I put that in the wrong spot. And then we had 10, 4. So kind of like that right there. So, and that is your original function. We called it gx. So I'll put that right here. Now let's talk about getting the inverse of this function here. You'll see a few of these square root ones, I think, on quizzes and tests as far as getting inverse. So I'm going to rewrite it as y equals square root of 2x minus 4. Alright, and then to cancel out a square root, well actually first of all I got to switch x and y, my bad. Getting ahead of myself there. Alright, but to cancel out a square root, we're going to square both sides. So this is going to be x squared and then equals, and then this stuff kind of takes care of itself right there. So that'll be 2y just minus 4 like that. Okay, and then afterwards, we need to add 4 to both sides. So that'd be x squared plus 4. I got to come over here to the other side. And then equals 2y. And then we're going to divide each piece here by 2. So you can kind of say it's, I guess, 1/2 x squared and then plus 2. Alright, and that is your new equation. Then now we're going to go back to the graphing calculator to go and graph it. And actually, we can go back to what we said originally about inverses. We said inverses is just you switch the domain and range values. So actually, that table that we had, we can use that same table to go and graph it. So instead of having 2, 0, we can have 0, 2. And then you had, I guess, 2, 4 right there. And then I guess you're going to have 4, 10. And notice that that's a reflection across that line y equals x, that diagonal line right there. Now, one thing I did want to note here, when you go and type 1/2 x squared plus 2 into the graphing calculator, it's going to show you something a little bit different, and I just want to hit on this here real quick. And this is kind of, pre-AP-ish as far as this idea here. I'm going to put 0.5 x squared right there. What do we got? Plus 2. And when you graph it, it's going to show the whole graph, which is kind of weird. Yeah, so it shows the whole graph, but we got to keep in mind the original function only had from 0 to, I guess, infinity for the domain value. So you're only really looking at these range values that start here at like 2 and then going up to infinity. So it's you almost have to disregard this left-hand side. But I always do the test. I always do the test. Sorry, I thought I closed out my thing there. I always do the test and see, does it look the same across that diagonal line right there. It needs to look the exact same, and then you're good to go. Okay, and then what do we got here is gx 1-to-1 explain. And the way I would explain that is remember, horizontal line test. If I draw a horizontal line anywhere, is it going to cross twice? It does not. So we're going to say yes. We're going to say because the inverse is a function, or even you could probably even say this, or yes because of the horizontal line test. There we go. Okay, so that is that there. All right, let's look here at this next section here, because we are about to evaluate, we're going to do some composition of inverse functions here. So we're going to recall some composition of functions here. So this is from the previous day here. So if you look here, notice here you got gx right there. So what that means is take your g equation and plug it into the f equation. So here's your g equation, and then we're going to plug that into the f equation. So we're going to do that to, remember we put parentheses, negative x squared plus 5, and I guess plus 3. And then we distribute, it's negative 2x squared plus 10, and then plus 3. And then combine like terms, so that's negative 2x squared, I guess, plus 13. Right there. Alright, and that was all I guess we needed to do there. Let's look at this next one here. This right here, this is saying take f and plug it into the g equation. So here's your f, and then you're going to plug that into the g. So that'll be 2 parentheses your x and then minus 7, but then inside the parentheses 4x was 9. So distribute, that's negative 8x plus 18. This might even be similar to an example we did earlier. 8x was this plus 11. Okay, So that is composition of functions. The reason we're going to do that here is there's something real specific about if you use composition of inverse functions. So by using a composition of functions to determine whether each pair of functions are inverse functions, both compositions should simplify to x. So if we plug in an inverse into its regular function, they should come out to x right there. And that's kind of what all that is saying right up here. So we're going to try it out here. So we're going to take fx, we're going to plug it into gx, and then we're going to take gx and we're going to plug it into fx. So let's see which one they want us to do first here. I guess gx, let's take g, plug it into f. So let's do that here. So you got 2, and then parentheses 1/2 x minus 4. There's your g function. And then close parentheses, still got the plus 8, don't forget that. And then we're going to see if this simplifies down to x. Okay, so 2 times 1/2, that is just 1. So we'll say 1x minus 8, but then you got that plus 8 right there. And those will cancel each other out, so that comes out to x. Okay. So now we need to go the other direction. Usually you want to show it both ways. I've never seen an example where it works one way and not the other, but yeah, usually it's a good idea to work it out both ways here. So now we're going to take fx right here, and we're going to plug it into gx. So we're going to take, I guess, 1/2 x minus 4, and then we're going to plug inside the parentheses 2x plus 8. We're substituting that in. Okay, so let's distribute 1/2 of 2x is x again. 1/2 of 8 is 4. And then you got minus 4, and then the 4's cancel out. So it'll just be x. So are these inverses? Yes, they are. Because they both came out to x right there. Okay. So let's verify and see if these two are inverses of each other. So they didn't really give us an order, so it doesn't matter. I guess I'll go f of g of x first, which means take g, plug it into f. So that would be this order right here. So we'll go 1/2, 2x plus 6, and then minus 3. Okay, distribute, simplify. What was that? X plus 3 and then minus 3. So that should be just x right there. So that one works out. And let's check the other order. Let's do g of f of x. I guess I'm kind of getting a little too far over, whatever. G of f of x, so f into g. So that's that into that. So 2 and then 1/2 x minus 3 and then plus 6. So x and then minus 6 and then plus 6. The 6's should cancel and then it's x. So these are definitely inverses of each other. Here's what I'm going to do. I'm just going to circle that. Move that over. Okay, and then let's see here, part B. Maybe this one doesn't work. I'm not sure. So let's do f into gx first. So we're going to go 1/3 and then 3x minus 2 and then plus 2. Now this one here, we can do 1/3 of 3 right there. That's just going to be x. But then 1/3 of 2, I guess, is just going to be 2/3 right there. Okay, and then we still have this plus 2 right there. So, and I think when you simplify that down, it's kind of like subtracting 2/3. I think that's like 1 and 1/3. But anyways, this is not x right there. Should have just been x. Everything should have canceled out. So we can already tell that this one is not, I guess these are not inverses of each other. And if you want to go and show the work for the other way, if we go and plug in, I guess, 1/3 x plus 2 into the other function, let's see what that would look like there. So we'll go 3, and then 1/3 x plus 2, and then minus 2 right there. So if we go and do that, that gives us x plus 6 minus 2, which comes out to x plus 4, and obviously that one doesn't work out as well, so these are not inverses of each other. So usually, though, if you can show that one way doesn't work, usually I would stop there. Alright, I think we got just a couple more here, so not too much. So show that the following are inverses of each other, kind of repetitive now. Let's see if we plug in gx, if that comes out here. So this one is square root of x minus 3 squared, and then plus 3. Now remember, when you got the square roots and everything, those will undo each other. Squares of square roots right there, so that should be x minus 3 plus 3 right there, so then that should be x there. Now let's check the other way. I think because we have just regular positive square root right there, that might mess things up here. Let's see what happens. So anyways, let's go do x squared plus 3 back into this thing. So we'll go and do that. What do we got here? Square root and then x squared plus 3 and minus 3. Alright, so then we can actually simplify these down here. Those should cancel out. So it should be the square root of x squared. So that does come out to x. So these should be inverses of each other. Right there. Now, as far as there's actually something kind of technical here, you have to restrict the domain for this, because one of these graphs, x squared plus 3, kind of looks like this right here. And then square root of x minus 3 looks like this right here. It's only like half of the piece. So if you wanted to kind of get into that pre-AP level, you have to restrict the domain. But I don't think you're going to see that like on a quiz or a test, so I wouldn't stress too much on that. Guess you would have to say your domain value needs to be from 0. If you wanted to get real fancy here, you'd say domain is from 0 to infinity, I guess. But honestly, if you know this right here, you're going to be good for regular algebra 2. So. Okay, next thing here is just finding the inverse of a formula. Essentially, most of the times that just means solve for the other variable. Okay, so earlier we found inverses, switch x and y, but if we're doing an inverse of a formula with like different letters, we can't really do switching in an x and y. So it just means solve for the other variable. That's just the big thing there. So instead of like solving for c here, like this has c by itself already, we're going to solve for r right here. So we're going to get r by itself. We can do this in one step, real easy here. We're going to divide by 2 and then pi on both sides. So r equals c over 2 times pi. And that's it right there. Super easy, nothing wild. Now b has got a little bit more going on here. I think this is your Fahrenheit to Celsius formula here. So we're going to solve for c, get c by itself. Now before we do something with this weird fraction, we need to move that 32 to the other side. So I'm going to do that. It should just be f minus 32 degrees and 9/5 c. Alright, something we learned back in Algebra 1. If you want to get rid of a fraction, you could divide by it, but we could also do something called multiplying by the reciprocal, or multiplying by the total opposite fraction. And that would cancel everything out. And we have to multiply this entire left side by that same fraction right there, 5 over 9. And some people are going to be kind of picky and want to simplify this, and some teachers are going to be fine with you leaving it like this right here. So I would leave it like that, but you could go back and distribute the 5/9. It is going to make it messier. So I would just leave it like that there. But big thing here, inverses with different variables and everything, just solve for your other variable, and you should be good. I believe that is it here for today.